Uh, okay, let's get started. So welcome to this course. This course is the GPU architecture course. So this course actually is the newly initiated course. But, so actually 2 years ago, I taught the parallel process architecture course. Okay, but the GPU processor is the parallel processor, kind of a parallel processor. So actually, I taught about the GPU architecture 2 years ago. So even though the title, the name of the course was changed, actually it's the same. Then in this semester, the parallel process architecture was also provided to students. But I believe the parallel process architecture course, the instructor will teach about the parallel processing, such as the parallel processing libraries, such as pthread or OpenMP. Then also he will teach about the cache coherence or memory coherence protocols. So actually, this cache coherence or cache also memory consistency is a little bit tricky problem in the multi-core architecture, but it's very important. Also, and then in this course, I will teach about the GPU architecture. So I believe everyone knows about the GPU because recently GPUs are very popular and everyone wants to buy GPUs, even though the GPUs are very expensive because of AI applications or neural network applications. So everyone knows that if we use GPUs for AI or neural network applications, then we can accelerate the performance of those kinds of applications. So which means that GPUs are very important recently. So then it's more expensive than high-end multi-core CPUs. Okay, so in this course, we will be exploring the research topics, and then also we will explore the hardware architecture and the software execution model of GPU process GPU. Okay, so this is the so I will introduce about this course. So object of this course. So actually, I highlight the hardware architecture and then software execution model of massively parallel processor. Okay, so in this course, I will focus on the hardware architecture. Okay, hardware architecture of GPU. So I will focus on the software execution model. So actually, GPUs are very different from the architecture of CPU. So I hope everyone took the advanced computer architecture course, but also I hope at least you need to take the computer architecture course for undergraduate student. So which means that I hope you have some basic knowledge on computer architecture or computer organizations. So let's review some knowledge of the computer architecture. So what is important for designing architecture or architecture of a CPU? So what is important? The performance, right? So we focus on the performance of CPUs or processors when we design the architecture of processors. So like it's obvious, because everyone wants fast CPU, fast processors. Then why do you use GPU? So as you can see, so the name of the GPU is actually the actual name of the GPU is the graphics processing unit, so which means that it is the processor for accelerating graphics applications. So actually, which means that GPUs were originally designed for graphics applications such as game, image processing, or video processing. But recently, GPUs are used for general purpose applications. So which is called the Common application. Okay, so actually we use CPUs for general purpose applications, which means that we can program our code with other languages such as C or C++ or Java, and then we can compile our programs using compilers, the GCC or some other compilers. Then we can execute these applications on CPU, and then I call these applications general purpose applications, which means that we can make any kind of application for CPU. So the CPUs can execute any kind of applications. So, and then I mentioned that, so recently we can run general purpose applications using GPUs. So that's why recently GPUs are called the GPU. So the first GP means the general purpose, and then the second GP means the graphics processing. So which means that we can write any code, any general purpose we can make any general purpose applications using GPU programming framework called CUDA. CUDA was developed by NVIDIA. Also, so AMD used OpenCL. So it's also general purpose programming framework for the acceleration of FPGA and GPU. So which means that we can make any application, and then these applications can be executed by GPU. But the architecture, we need to focus on the hardware architecture of GPU because the architecture is very different from CPU architecture. So as I mentioned, as I asked the question, so why do we focus on the research on the CPU architecture? So what is the purpose of CPU architecture research? Performance, okay, performance and cost. So actually, CPU is if you took the advanced computer architecture course in the last semester, then I focused on the out of processing architecture of CPUs, which are modern architectures of modern CPU processors. So actually, CPUs focus on the performance of single thread, and for GPU architecture, we focus on the performance of parallel processing applications. So it's different. So it means that the design purpose, the design policy of GPUs are different from those of CPUs. Okay, GPUs are designed for originally it was designed for graphics applications, but now it is designed for general purpose applications, but general purpose parallel processing applications. So which means that we need to know the hardware, the unique hardware architecture property of GPUs. Also, software execution model. So if you are interested in GPUs, then you can find that our GPU card, a GPU chip has 1,000 cores, or even recently the high-end workstation GPUs have 10,000 cores. And then actually it's ridiculous. So think about the server CPUs. So actually, the Xeon Platinum, which is the most expensive, high-end server CPUs. Xeon Platinum also, even Xeon Platinum has only 30 to more than a little bit more than 30 cores. But compared to this Xeon processor, which have 30 cores, GPUs, a single GPU chip has 10,000 cores. But 10,000 cores. Is it possible? But you know, the GPU chip also it's a very large. It's very, actually recently the biggest chip is the AI acceleration chip. But before developing AI acceleration chip, the GPU was the largest chip. But even though GPU chip is the largest chip, but 10,000 cores in a single chip, it sounds ridiculous. Then, what is different? What is different from the core of CPU architecture? So you need to know if you take this course. So actually we focus on the hardware architecture, the unique hardware architecture of GPU, and then we will learn how these 10,000 cores, thousands, or so actually 3 or 4 years ago, I mentioned GPUs has hundreds of cores, but recently GPUs have thousands of cores. Okay, so and then we will learn how these thousands of cores are organized in a single chip of GPU. So we will focus on the hardware architecture and then unique other characteristics of GPU architectures. Then software execution model. So I mentioned that GPUs are designed for parallel processing applications. So and then also I mentioned that GPUs have a single GPU has 10,000 cores. Then we need to run our applications using these 10,000 cores, 1,000 of cores. Then how can you organize our software? How can we run our software using these 1,000 of cores? So basically for parallel processor. So actually you have to use these many cores. With the many cores, then GPU has also provided a unique software execution model. So actually, NVIDIA provides the CUDA primer. Then CUDA programming is very similar to the C programming, but in order to work the parallel processing architecture of the GPU, the CUDA also supports some unique programmer or unique software programming model for GPUs. So we will learn about this unique software execution model of a GPU. So these are two main purposes of this course. So what do we cover in this course? As I highlighted in this slide, so we will focus on the hardware architecture of the GPU and then software execution model of GPU. And then in order to learn about the some GPU's execution software execution model, then I will briefly. So in this course, I will just cover the basic programming model of the GPU, so like NVIDIA. Basic programming model provided by NVIDIA CUDA. And then we will learn about the GPU architectural simulator. So my research area is the computer architectures, and then I frequently use the architectural simulator for my research because, think about this. So we cannot modify this large GPU chip. Okay? We cannot, it's actually, in order to make a single chip, then actually we require many engineers, a large number of engineers. But in the academia field, it's not possible. It's not possible to design this very large chip like GPUs. So it's very hard to modify the GPU architecture and the real GPU chip. So we use the architectural simulator, which emulate the cycle-based behavior of GPU architecture. So I will introduce about this GPU architecture simulator for the GPU scene in this course, and then also I will provide some opportunity for doing a project using this GPU scene. Okay. So simulator is kind of a software, so you can modify any code, or so you can read the code in the GPU simulator. Then I will briefly introduce about the GPU hardware profiler. Then, as I introduced in the syllabus, so we will review the recent research papers in GPU research area. Okay. The textbook. So for this course, I will use the lecture slides, and then also, as I mentioned, I will introduce some GPU research papers. Okay, and then so this is and then if you are interested in GPU programming and also GPU software execution model, then you can read this. So the programming massively parallel processors written by David Kirk and then Mei Hu. Mei Hu is the professor at UIUC. Okay. So if you are interested, and you can read this book. Okay. So because the GPUs are actually GPUs have been used for general purpose applications recently, and we cannot find good textbook for this GPU course. So I think this is the only textbook for GPU programming model. And then actually you need to read papers if you are interested in GPU research. Okay, so you need to read many papers. Okay, the course material. So I will use the lecture slides like this, and then we will use GPU simulator, and then for some assignment, I will provide the Docker environment for GPU simulator. So, but I will not explain about how to use Docker. So, if you so you need to learn by yourself for Docker environment. Okay, but it's very convenient. The prerequisite, so recommended, as I mentioned, you need to have the basic knowledge on computer architecture. So at least you need to know about the pipelining or 5-stage pipeline process architecture, and then memory hierarchy, the basic memory hierarchy for single core architecture, and then advanced computer architecture course. So it was provided last semester. And then, so as I mentioned, CUDA framework is very similar to C. So that's why the CUDA is called the CUDA C. Okay. So you need to have basic knowledge on programming languages such as C and Python. Okay. Also, the GPU sim, the simulator is written in C++. Okay, so if you want to modify the GPU scene, then you need to have knowledge on C or C++ languages. And then basic knowledge on Linux operating system and Docker. And then, as I mentioned, we will use Docker container environment for installing GPU scene. Then usually the Docker runs on Linux operating system. So you can run Docker on Windows using WSL, Windows Linux. Windows subsystem for Linux, WSL. But that actually originally Docker was developed on Linux environment, so you can use the Linux operating system, and it will be good. So the so and then I will introduce myself. My name is Gondel. So you can find my information such as some information, useful information such as office hours and then my email address, and also you can find my web page. So, and then as I mentioned, I provide this course for students who are interested in computer architecture research. Okay, so I will provide some knowledge, required knowledge for the related research field like computer architecture or computer system architecture. So if you are interested, you can also visit my web page. So actually, I did not update my personal web page for a long time. Please visit my web page for recent research work and by my research lab. Okay. So my research area is the computer architecture generally. So general computer architecture research area. And then I focus on the process architecture such as the GPU and then memory storage systems, accelerator architecture, and then secure process architecture. Okay. So you can find many architecture here. So my research area is the computer architecture. And then for this course, I will use the Blackboard. So and then I will post some important announcement on Blackboard. Then I believe if I post the announcement, then the announcement will be emailed to you. Okay. Also, I will post some homework assignments or project for this course, and I will post the slide. But I recommend you to use Piazza. So actually, for the graduate course, I made Piazza for every course I taught. But undergraduate students made use of Piazza, and then they post some questions or they post some comments on the Piazza. But I found graduate students did not make use of Piazza. It's just so silent. But for this course, I also made the Piazza environment for this course. And then you can sign up Piazza using this Atlas code, GPU or you can join as a student. Okay. So actually, for this course, after this course, I provide some additional papers you can read for GPU architecture. Then I already post some papers on GPU research area on the Piazza. Okay. So if you visit the one student was tested positive. I will share how I use Piazza. So, okay. So as you can see, I already posted 2 rental slides about this Piazza. So you can find the resources tab here. Also, you can find the resources section here. So I posted 3 papers regarding compute research. And then actually these papers introduced about the basic architecture of GPU. So I hope everyone reads these posted papers. Okay? So I will use the Piazza for the resource sharing also. And then you can post any questions on Piazza. I found no one made the use of Piazza for the graduate course. Okay, so then grading is a tentative grading policy. So we will have one midterm. Actually, after I teach the basic concept or how the architecture of the GPU, then we will take the midterm exam. And so we have only one exam for this course, and so we will have the term project, the final exam period. So the project will occupy 30%. So it's a tentative. So it's not the fixed fractions. We will have one top project. So I will provide several assignments for this course. So we will introduce the paper, research papers. So you need to review some papers. Okay. Then exam is really the on-site exam, even though we are amid the COVID-19 pandemic. So now COVID is as a COVID virus. I think the COVID virus is the same, but everyone thinks that COVID now, the COVID virus is not severe, hopefully. So we will have the on-site exam, then this exam is a closed book. If you cannot use any electric devices, obviously, tuning, resulting. But you can answer in Korean for the exam. So actually, so this is the English course, and then I will majorly use English for teaching, and then also I need to provide every materials using English and Korean. So which means that I need to provide problems in English also exam. So this is my duty, which means that I need to use English for every materials, every teaching for this course, but you can use Korean, okay? You can answer in Korean, you can ask a question in Korean, you can answer in Korean, and so it's okay, it's possible. And then it's also easy for me. It's a tentative schedule of this course. So as you can see, after teaching the every basic concept of the GPU architecture and software execution model, we will take midterm. So sometimes the scheduling is changing. So maybe this exam date can be postponed, but I scheduled the midterm exam after the lectures for GPU hardware architecture. So then we will have paper reviews for the research field here. Then also I will provide some project topics, and then around this, and you can present your final project result in the final exam period. Okay, and then fortunately, we don't have any holidays during the whole semester, so yeah, I can provide classes without any tests. Any questions about the syllabus? 질문 있나요? 말했듯이 질문이나 이런 거 Okay, also Oh, I guess sorry for syllabus. Okay, so this is the first class of the course, and then I will. So actually, I introduced about this course. Now, so I will introduce about the GPU architecture. Okay, so don't worry. So I will and this the first class will end before the regular class time. Okay, so I quickly introduce about the GPU architecture and then why GPU is important for recent computer systems, recent high-end supercomputer systems. Okay. So, okay, let's start from the computer architecture 101. So it's a basic concept of computer architecture. Okay, I make several questions. Actually, I already asked this question. Why do we study on computer architecture? So what is the goal? What are the goals of architecture research? And then obviously we want to make better processors. Yeah. What does better processors mean? What does making better processors mean? So actually for the research, we need to focus on the high performance, and we need to focus on the cost of our computer systems. So so we are engineering students. So every engineer focuses on cost and performance. Okay. So which means that if you write a paper or research paper, then usually you need to focus on the performance and cost of your ideas for your result. So which means that you need to provide the result that compare the performance of your idea with the previous result. Also, you need to compare the cost of your idea. It's very important. So two factors of your computer architecture research. Then let's start from the very simple process architecture. So as you can see, this is the single-cycle processor. Okay, so what are the issues on single-cycle processor? So why do we not? Why? So think like, so why we do not use this single cycle processor? So actually this is very simple, and then it's very, you can make this single cycle processor very easily. But why we think like why we don't use single cycle processor? So what's the matter? So I mentioned CPI or IPC. So I believe everyone knows about the CPI. So clock per instruction, the IPC is the instructions per clock. Now what is the CPI of a single cycle processor? Clock per instruction. It's one, right? Actually, single cycle processor takes one clock for every instruction. Okay, the IPC is 1. Also, because the IPC is the 1 over CPI. Okay. So if we just focus on the CPI, then it's okay. It's just 1. And then what are issues on the single cycle processor? It's performance, right? Because when we measure the performance, we measure the execution time of certain application executed on computer systems. Then how can you measure the execution time? Let's see, time TEXE is the instruction count multiplied by CPI multiplied by T. the clock period. Okay, the CPI is 1, the instruction count is determined by our application and then compile options. Then T is critical for the performance because T, the clock period, is proportional to the execution time. The execution time is determined by clock period. Then what is the problems of this single cycle processor? T is very large, right? So because the critical path is very long, the single cycle processor, the clock period is also long, which means the execution time is increased if we use the single cycle processor because of this clock frequency, the clock period. Actually. So we cannot use single cycle processor. So we use. So this is the figure of 5-stage pipeline processor, and then as I mentioned on the title of the slide, this is the statically pipelined processor. You need to focus on the statically. So what is the CPI? What is the IPC of this processor? CPI, clock per instruction, is so theoretically the CPI is 1, but because of hazards, the CPI is bigger than 1 if we use the statically pipelined processor. Why? Because the clocks are wasted because of hazard such as structure hazard, data hazard, and control hazard. Okay, so it's very important, right? The hazards are very important because of hazard, the performance of processor is degraded because the clock cycles are just wasted. Okay, so when we design a processor, we assume that our processor, a single processor, can execute 1 instruction per cycle. It is applied. Actually, the single cycle processor can execute 1 instruction per cycle. But because of this critical path of the single cycle processor, then we design a pipeline processor. So the benefit of the pipeline processor is that we can cut down the critical path. Okay, so which means that it's the delay of the project. So we can reduce the longest delay of our data path. Okay, but the CPI is increased. The CPI is increased. The CPI is actually bigger than 1 because of hazard. Also, actually, I did not consider about the memory here, and then also you can find the data memory here and the instruction memory here. And then actually, these memories are caches, not real memory. So actually, these memories are cache memories. And they actually level on cache, right? So, and then if the data is not found in this level on caches, then we need to access level 2 or last level cache, or even the requested data is not found in last level cache, then we need to access memory. Okay, so actually, for the load or store instruction, some load or store instructions may take more cycles for accessing data, the memory hierarchy. So usually the CPI is bigger than 1. Then what is improved compared to the single cycle processor? we can improve clock period, which means that we can decrease the clock period. So which means if we see the also is IC, CPI, T, so we can reduce this part. So we can increase the performance. So we can improve the performance using pipeline architecture. Okay. So, but problem CPI, because of hazard, the clock cycles can be weighted. Then because of hazard, the CPI is also increased. So CPI is increased like here, and we know that execution time also increased, and then the performance is the inverse of execution time, right? So it means the performance is irrelevant. And then just so think like this. So I mentioned that we assume our processor can execute one instruction per cycle. Okay, but this assumption is broken because of hazard. Then why the hazard? So what is the reason of hazard? So there are three types of hazard: the structure, control, and data hazard. But actually, the data hazard are critical. Also, the control hazard are critical actually. But program side, data hazard are called the true hazard because data hazards are caused by our program code. Okay. And then if data hazard, like the data hazards are caused by data dependencies between instructions. And then if the data hazard encountered, then this processor cannot execute instructions. Okay, that's the problem. It's a critical problem of the processor. Yes. So the computer architect, not we. So computer architect proposed out-of-order processors. Also, the problems of this statically typed processor is that this is the in-order processor. What does that mean? Every instructions are executed in order. Okay, and the problem is that load stored, actually load instruction. So I mentioned that if the load is executed and then if the demanded data is not found in cache, level of cache, then we need to wait until the data is transferred from the low level cache or memory. Then load is here and then following instructions are in these pipeline stages. But because of this load instruction, following instructions cannot be executed. So if the following instructions are dependent on this load instruction, which means that the following instructions can use the data from this load instruction, then we can start the execution of these instructions. But if the following instructions are not dependent upon this load instruction, we can execute these instruction. But because this statically pipelined processor, we cannot execute the following instruction because every instruction needs to be executed in this processor. So clock cycles are wasted. So we don't avoid this situation. So computer architect developed the out-of-order processor Actually, the most of modern processors have most of the modern processors have this out of the processor architecture. So which means that the instructions can be executed out of order. So which means, so this is the instruction 1, 2, 3, 4, 5. And then let us talk the instruction 1 is the load instruction, and then this load instruction is accessing data on the memory. So this load instruction will take very long cycles, but following instructions like add, sum, multiply. So let us assume that these instructions are not dependent on load instruction. Because these are not dependent, these instructions can be actually executed. So also we can get result from these instructions. And if we can get result from this instruction, some following instructions that use the result from these instructions can be also executed. Okay, so with the out of processing, then we can solve the issues of statically controlled pipeline process. Okay, so which is the in-order processor. So then what is the main idea? What is improved with the out-of-order processor compared to in-order processor? What is improved? So what is it improved? It's very important actually. So we developed our process architecture for improving performance, right? It's obvious. And why the performance is the performance improved? Why? What is science? Yeah, right. The CPI is improved, so which means that we can reduce the CPI. But yeah, right. With the out of the processing, so we can. So answer is that we can increase the number of instructions which are executed concurrently in this processor. So we can increase the number of concurrent instructions in our order processor. It's very important. So actually, with this out of the processor, we cannot solve low hazard, the read after write hazard. We cannot solve because low hazard are true dependent. Low hazard is the true dependency hazard, which means that this low hazard is caused by program, the code. But there are different types of hazards, such as the wow hazard, right at the right hazard, and the war hazard, right at the read hazard. This type of hazard are caused by processor architecture because of the lack of registers or some different execution time of by this execution units. So also the out of the processor waste cycles because of war hazard and wow hazard and war hazard. And actually is out of actually in this statically pipeline processor, we don't need to consider about the war hazard and the wow hazard, but because in another processor since the instructions are executed in order, and then if the one instruction is blocked in a certain stage of the pipeline processor, then following instructions are also stored in the other pipeline stages. So in the out of the processor, if these instructions are independent on this former instruction, then these instructions can be executed. So it means we can increase the number of instructions concurrently executed in this out of the processor. It's very important. Okay. Why do I explain? Why am I explaining this? Because I want to compare the design policy of the GPU architecture and the CPU architecture. And then another improvement is the superscalar. What is the superscalar? What is the meaning of the superscalar? With the superscalar, we can dispatch multiple instructions per clock. Okay. So actually, if we design a simple out of the processor, actually this type, so I know that's so originally this out of the processor can execute one instruction per clock. So which means that actually the instruction is enqueued in this instruction fetch queue, and then the instruction is dispatched by this decoder and dispatch unit. And then this instruction is delivered to this issue queue of the execution units. So as you can see, this processor has three different types of issue queues, like the integer issue queue, memory type instruction issue queue, and the floating point issue queue. But with this processor, we can dispatch one instruction per cycle to target issue queues. That's fine. What is the issue? So we need to think about the performance. So I said that with this processor, we can dispatch a single instruction per cycle to this figure 3 issue queues. That's the problem. So it's like this. This is task, and then but there are 3 workers, worker 1, worker 2, worker 3. But task is only 1. Then we can provide this task to the worker 1. Then how about these workers? These workers do nothing. So which means even though this processor has many other execution units, instructions are dispatched to multiple execution units, but only one instruction is dispatched, issued to execution units. It's very similar to there are multiple workers, but we have only one task. So this only one task is provided to one of multiple workers. So in this case, other workers do not. The computer architect cannot endure this situation. So we need to provide tasks to other workers. Okay. So how can we provide task to which means the instruction to other execution units? So we can dispatch multiple instructions. That is the idea of superscalar. So with the superscalar, we can increase the number of instructions that can be issued to execution units. Okay, which means that, so for example, this is the full way out of the processor, which means that this processor can dispatch 4 instructions per cycle. Okay. So then what is the CPI? Theoretical. What is the theoretical CPI for this full way out of the processor? Which means, let's think about the IPC. So theoretically, if there are no hazard, then for the full way out of the processor, the IPC is 4, right? Because 4 instructions can be executed. So 4 instructions are dispatched every cycle, and if these instructions can be executed, then the IPC is 4. So let's compare with the other old processor architecture. So single cycle processor IPC is 1 because the CPI is 1. Then statically pipeline processor, theoretically IPC is also 1, but because of hazard, the IPC is smaller than 1. The CPI is bigger than 1. Okay? And then out of the processor. So actually, I mentioned that the statically pipeline processor, the clock cycle is very speedy to in other application. Okay. And then with the out of the processor, we can resolve this issue. So we can mention that the independent instructions can be executed out of order. Okay. So CPI is improved, which means that we can also improve the IPC with the out of processor, which means we can increase the number of concurrent instructions. And then with the superscalar, we also increase the number of instructions which are executed concurrently in the processor. The IPC is also increased. So theoretically, the IPC is the same to this number 4A. Okay. So why did I explain this? So we can increase the performance. So actually this I explain about the history of CPU architecture, and then computer architects propose advanced architecture for improving performance. But until this slide, we can improve the performance of processor with ILP. So you need to memorize this terminology, ILP. So ILP means instruction level parallelism. So what? Because as I mentioned, we can, with the advanced processor architecture, we can execute more instructions. So more instructions are running simultaneously. So I mentioned concurrent instructions. So more instructions can be run simultaneously in a processor. So if we increase this concurrent instruction, number of concurrent instructions, then we can increase the IPC. You know, the IPC is the inverse of CPI, and then T execution is the instruction plan, CPI, and T. So, and then as I mentioned, the instruction count. So instruction count is the software part. Okay, the hardware cannot decrease the instruction count. It's the task of software engineers. But architect can improve CPI and clock period. And then usually the architects can focus on CPI. So if the IPC is improved, the instruction per cycle, and CPI is decreased, so which means that execution time is decreased. So we can improve the performance. So instruction level parallelism means that we can, with the advanced architecture, we can improve the we can increase the number of concurrent instructions. Okay. So think like this n-stage pipeline architecture. The n-stage statically controlled pipeline architecture. So if you see the pipeline architecture, for example, 5-stage pipeline architecture, then you can observe there are theoretically one, two, three, 4, 5. So theoretically, with the n-stage pipeline architecture, we can observe 5 concurrent instructions which are being run in the processor. Okay, so with the pipeline architecture, we can increase the instruction level parallelism. Then with the out-of-process architecture, also even with the superscalar processor, we can increase the number of concurrent instructions, which means that we can improve the performance with the instruction level parallelism. So which means more instructions are being executed concurrently in a processor. Okay, this is the mainstream, main research stream in CPU field, CPU architecture field. So with the CPU, then traditionally, I said traditionally, so with the CPU architecture, we focus on improving ILP, instruction level parallelism, to improve the performance. Now, what are the issues? So we can achieve higher performance. It's a benefit from more higher ILP, instruction level parallelism. But as you can see, compared to things like processor, the architecture of pipeline processor is more complicated, more complex. Out of a processor, it's not easy to understand. It means that it's more complex. And the superscalar or have. So what's the problem? We require more complex structures. We require more complex architectures to improve ILP. That's the problem. Complex architectures, and we require more complex logic, data logic, and then which means we require more hardware resources. These hardware resources will consume electric power, which cost. As I mentioned, we need to focus on performance and cost of our processor. These are the two main goals of the engineering researches. So power is a critical issue of the issue of improving instruction level parallelism. Okay, so as you know, it's very hard to understand. It's even more. It's like more hard. It's harder. Very difficult to understand. But so with the so for improving instruction level parallelism, then we require more complex architecture, and then even like this. So complex starts to focus on PLP. It's called the thread level parallelism. Okay, so compared to instruction level parallelism, only this part is changing. The thread level parallelism. So what is the meaning of TLP, the thread level parallelism? So with the IFP, so we can say that improving instruction level parallelism means we can increase more instructions, the more we can increase the number of concurrent instructions in the processor. Then, right? So which means the meaning is very similar. So which means we can increase the number of concurrent threads. So which means multiple threads are running simultaneously in a processor chip. Okay, that is the meaning of thread level parallelism. So actually, this IFP that we can improve the performance of single thread, right? Because we can increase the number of instructions which can be executed in the processor. And then, in a single thread, there are many instructions. And then if more instructions can be executed, then we can improve the rate. So we can reduce the latency of the single thread. But with the thread level parallelism, we can increase the number of concurrent threads, which means that we can increase the number of threads which are executed simultaneously in a processor. Okay. So with the thread level parallelism, we can achieve higher throughput, that latency, and then we can benefit from parallel processing. So actually, the CPUs also exploit thread level parallelism to improve the performance, which means the throughput of the CPU. So we can apply the multi-threading, so which means that multiple threads can be executed in a single core. Hyper-threading, right? So actually, the Intel developed hyper-threading, which is actually the simultaneous multi-threading, which means that with a single physical core, the single physical core can run multiple threads, usually 2 threads concurrently. This is the multi-threading. And then chip multiprocessor, which is the multi-core. So as I mentioned, the server CPUs have multi-core architecture, and also even the personal use CPUs, such as the Intel I series, has the multi-core architecture. So which means that the core is the independent processor. If we have multiple cores, then we can run multiple threads concurrently. So with actually the modern CPUs also exploit the thread level parallelism. So why did I explain about the thread level parallelism? Because GPU also exploit TLP, the thread level parallelism, to improve the performance of parallel process. Okay, that's why the GPU architecture is different from CPU architecture. Okay? So let's compare the GPU briefly. What is different? So which processor is there? So it's outdated. Xeon or NVIDIA Tesla. So which processor is there? So this is the question I asked the first day of class in the undergraduate computer architecture course. Xeon and NVIDIA Tesla, which processor is there? Which processor is more expensive? Tesla, CPU. So recently the CPU price is higher than the CPU price. And recently because of many reasons, such as the cryptocurrency and some other reasons, the tsunami. But the NVIDIA Tesla is more expensive. But can you say that NVIDIA Tesla is better than Xeon? The performance is higher. So we cannot compare directly the performance of Intel Xeon or NVIDIA Tesla. So actually, if we just focus on the throughput, like such as the floating flops, like floating operations per flops per second, like number of floating instructions per second, then the performance of NVIDIA Tesla is higher than Intel Xeon. Because we can just focus on the number of floating operations. So it's similar to the throughput, not latency. So the recent GPU has also 10,000 cores, and then Intel Xeon has 330 cores. So if we just compare the number of cores, GPU has more cores. Okay? So with the more cores, GPU can achieve higher flops. Okay? But we cannot compare the performance of Intel CPU or NVIDIA GPU directly because architecture is different. And then we select these processors based on the target applications. Okay? Okay. Let's move on. Let's compare the stock price of Intel and NVIDIA. So I also showed this slide. Past course for 2020. So as you can see, the stock price of the NVIDIA is higher than $500. It's about $50. So which means the NVIDIA stock price is 10 times higher than the Intel stock price. So which means NVIDIA is the company, or and then this stock price also reflect some popularity of the NVIDIA GPU, which means the GPU is also GPU becomes the very important processor in computer systems. Also, I checked the stock price of Intel and NVIDIA yesterday. Just the thing. Intel price is 130. It's 130. So if you have NVIDIA stocks, you are very unhappy. But it's the same to Intel. So actually, so actually around here, Intel was about 50, and then around here, around here, it was very high. Here. Oh, okay. But yeah, still the NVIDIA stock price is higher than the Intel, but because of the market situation, such as because of the high interest rate of the USA Federation, stock price of dropped. Okay. But the NVIDIA stock price is still higher than Intel stock. Okay, so which means even the stock price dropped recently, support 2000. The GPUs also becomes the GPUs become mainstream processor, control systems. Okay. Okay. So until now, I explained about the parallelism. So with the parallelism, we can improve the performance. So I explained about the instruction level parallelism and thread level parallelism. So for the instruction level parallelism, then we can increase the number of concurrent instructions. But as I said, not to improve the INP, then we require more complex architectures. Also, which means we need to invest more hardware resources for processor design with the TRP. So we can also improve the performance with trilateral parallelism. Okay, which means that we can increase the number of cores. So simply, if we increase the number of cores, then we can improve the TRP, trilateral parallelism. That's why GPUs have 10,000 cores. That's the highest GPU actually. So GPUs have thousands of cores to improve the trilateral parallelism. Okay. So I summarized some techniques to increase for increasing the instruction and parallelism here. Okay, also I summarized some techniques for improving trilateral parallelism. Actually, in the CPU domain, we use the simultaneous multithreading, then chip multiprocessor or many core architectures, the CPU domains. And then in the GPU domain, we use the SIMT architecture. It's called the SIMT. So, what does SIMT mean? SIMT. So, based on the Bliss taxonomy, you can hear SIMD. So, single instruction multiple data. SIMT, the T means the thread. Okay. So, GPU employs SIMT architecture. So single instruction, multiple thread. So actually, this SIMT architecture is very similar to SIMD, but GPU supports the divergent execution path to different thread. But these different threads share the same instruction. So that's why GPU architecture is called SIMT architecture, single instruction multiple thread. So I will also compare the SIMT and SIMD in the following classes. So don't know what the meaning of SIMT. So but just to remember that the GPU uses the SIMT architecture. The performance issue is that without this parallelism, we cannot improve the latency of single thread performance. So which means even though we can run many threads concurrently, we cannot improve the performance of single thread with the parallel process architecture. And then because CPU has the many VP cores, so which means that the low performance cores. So for the CPU domain, computer architects may have made efforts to improve the performance. So which means that they have improved the instruction level parallelism in the advanced architecture. But in order to pack many cores, which means the size of these cores should be very small, just small compared to the cores of the Xeon CPU. So the chip size may be similar, but the core is very wimpy. It's a low performance core. So because the GPU has the wimpy cores, the performance of the single thread is much worse compared to CPU. That's why we cannot run operating system with GPU. If you just run the parallel processing applications, not operating systems. Okay, so that's why the GPUs are called co-processor. The main processor is the CPU, but GPU is designed for accelerating parallel processing only. So Intel Xeon. Intel Xeon is also the server CPU, so Intel Xeon has multiple cores, but Intel Xeon is good for single thread performance. So Intel Xeon is the mainstream processor for computer systems. So main processor that runs the operating system. Also, Intel Xeon can execute single thread very quickly. NVIDIA Tesla GPUs is designed for graphics applications and parallel processing applications. So it's good for the many thread applications and good parallel processing applications. Okay, so target domains are different. So we cannot compare the performance of a CPU and GPU directly because target domains are different. Okay, this also I had this. So as you can see, number of total core is 40. And Xeon Platinum 83, 80. It's very large. And then total thread, so 80. So because of the multi-threading, so hyper-threading. So the maximum frequency is the 3 gigahertz. Okay, let's see the recent NVIDIA RTX A6000. So this NVIDIA processor has 84 SMs, and then CUDA cores per SM is the 128. So total number of cores per GPU is over 10,000. So compared to this number is 40. Then even though if we can compare the number of total thread and the number of total concurrent thread in the Xeon processor is 80. So 80 versus 10,752. Oh. If we just focus on the number of cores or GPUs are much better compared to the Xeon processor. But as I mentioned, these cores are very weak core. Actually, the core, the core of the GPU is similar to actually execution units in CPU. Okay. Then, recently the GPU frequency is also increased. The early generation GPU is the clock frequency was less, it's lower than 1 gigahertz. But recently, GPU also improved to 1.8 gigahertz. So compared to the CPU, the frequency is also low because of power consumption. Okay. So the chip size is very large, and if the clock frequency is high, then this chip will consume much power. If you add GPU card, then you need to also replace power supply, right? Because GPU consumes very much power. And the TDP of the Intel Xeon processor is also high, the 270. GPU also consumes much power. But if we increase the clock frequency of the GPU, then GPU will consume about 1,000 watts of power. Okay. Then compared to the CPU architecture, so out of the processor architecture, GPU architecture is different. So I will explain about the GPU architecture in the following classes. And also usage scenario, so domains are different. So CPUs are good for complex control flow dominated workflows. So which means the single thread applications, but general purpose applications include many control instructions, like branch instructions, or conditional branches, or jump instructions. So, in order to increase the performance of the single thread applications, a single thread which includes many control instructions. The CPU, actually, the CPU architecture include many techniques, many architectural techniques such as the speculative execution, the superscalar, out-of-loop processing, something like that. So actually, the CPUs are good for complex control flow dominated workload. But these techniques are eliminated. So these architectural techniques are removed the GPU architecture, which means the GPU processor does not support out-of-order processing. GPU does not support speculative execution. GPUs can support branch instruction because that's why the GPUs are called the SIMT architecture, but this support is very limited. Okay, so if GPU applications have control flows like branch instructions and if as something like that, then performance will be degraded very much because GPUs does not support any speculative execution or branch prediction. So very advanced techniques for improving the performance of CPU, but these techniques are not applied on GPU. But then GPU supports the many threads. Okay, domains are different. Okay, so this is some tutorial. So some report from the NVIDIA. So the data about that. So actually, traditionally in the CPU era, the CPU performance is also improved exponentially. But we are facing the end of Moore's law. That's the problem. So yes, the CPU performance of the single core CPU is also saturated. So and then we assume that we can say that it's very hard. We can improve, but it's very hard. It's very hard to improve the performance of CPU because we are facing the end of Moore's law. But GPU has the SIMT architecture, that is a different architecture. So NVIDIA advertises that GPU, with the GPU, then we can improve the performance. So the future is that the Moore's law continue, can continue. Okay. But this is the advertising from NVIDIA. So, but the early paper, which is the paper. But as you can see, it's a GTX 20, and then in the Core i7, the early generation of the Core i7. In this paper, the authors compare the performance of the general purpose applications. EJK is not by application. So they compare the performance of the general purpose application, and then they reveal that the performance can be improved using general purpose GPU. Okay. The geomean is about the 2.5 gigahertz. Core i7 is also multi-core, but it's very early paper, as you can see, as it explained. Then, if we see the top 500 list, the top 500 is the highest, the ranking of the supercomputers. So we can find many GPUs are deployed in the supercomputers, the high-end supercomputers. So in 2019, we can find five supercomputers system with GPUs. And then in 2022, we can find 7 supercomputer systems which equip GPUs. So which means recently the GPUs are also used for supercomputers. So I summarize. Okay, so I will cover until this slide. So I will summarize the GPU. The GPU architecture becomes now. GPU architecture becomes the mainstream of the computer architecture research, computer systems actually. So, but as I mentioned, domains are different. So we cannot run operating system using GPUs because GPUs are designed for accelerating parallel processing only. So with the GPU, we can increase the throughput of parallel processing applications, such as the neural networks or AI applications. But if our application includes the very complex control flows, many branch instructions, then performance will be significantly degraded if we use GPUs. Okay, because domains are different. So original GPU was originally designed for graphics applications such as the pixel by pixel image processing, and then matrix computation. But recently, GPUs are great gadget for parallel executions. Okay, then actually the design policy is different, the business and architecture are totally different. So we need to learn. About the GPU architecture in this course. So as I mentioned, I will introduce some unique architectural feature of the GPU, the hardware architecture. So the software execution model, the GPU in this course. Okay. I hope I plan so I can complete the first class in 1.5 hours. Okay. So this is the first class. So I will stop here. Then the next class I will cover some. I will also introduce about the GPU architecture more. Then also I will review the basic architecture of the GPU and other processors before explaining about the GPU architecture. Okay, any questions? Thank you for your attention. See you in the next class. Have enjoy the 추석. 감사합니다.